Today we're going to look at graphs of linear functions. So linear sounds like the word line, which is exactly what we're looking at. We're looking at graphs of lines. When we talk about a linear equation, the form is going to look something like this. It's going to be y equals whatever your rate of change is. We'll talk more details about rate of change in just a second. That goes next to the x, and then you're going to have plus or minus, depending on if it's positive or negative, your 0th term. So if you're thinking to yourself right now, this looks really familiar, it's because it should. This is the exact same as the explicit equations of arithmetic sequences. So these concepts do overlap. They should feel pretty similar. When we talk about rate of change is the same concept, same idea as the common difference. But we're going to expand it just a little bit. So when we talk about the rate of change, when we're talking about how something changes, especially when we're looking on a graph, we look at what we call the change in y, so any vertical change, over the change in x. And a shorthand way to write that, we use this little triangle, that's the Greek letter delta. Delta y over delta x is a notation that you may see, just to shorthand it. So the change in y over the change in x. When we have a positive rate of change, we are increasing. And when we have a negative rate of change, we are decreasing. So we're going to use a couple graphs and kind of analyze the things that we can get from them and how we would want to use their equations. So if you have not printed out the notes, you may want to pause right here and copy the graph. While you copy it, I'm going to talk through what you should see on the graph. So we're looking at over time, what happens to a distance. And notice our units are included for us. We've got the time is in seconds and the distance is in meters. So we can see that whatever we're measuring here, our distance is increasing as time passes. It's going up. First question we want to answer is, what is the distance at the beginning? This is the exact same idea as the 0th term. So at the beginning and the 0th term are the same idea. And to pull that from a graph, we look right here on the y-axis. So that signifies the beginning or the 0 term. We'll start using the words at the beginning. You may also hear the words initial. And as we move away from sequences, where do we say 0th term? So the distance at the beginning was 2 meters. And I'm pulling that right from that green point on my graph. And then for the rate of change, we're looking at how we change over time. So what I like to do is pick out my next, I'm going to call it a nice point. And when I say nice point, I mean one that just lines up nicely with my grid lines. So I'm going to pick this point right here, the 0.13. And we said that rate of change was going to be the change in y over the change in x. So what we're talking about here is to get to the next point, I go up 1, positive direction, and then I go over 1. So for every increase in 1 second, my meters increase by 1 as well. So my rate of change, or the common difference, is 1 meter per second. And I'm going to use that little dash. That's a notation you've probably seen before, meter per second. So with each second, my meter gets increased by 1. So when I go to 2 seconds, I go up another 1, another 1, another 1, and that's why my rate of change is 1 meter per second. When we write an equation, this is going to set, we said, looks just like the explicit for an arithmetic sequence. So we would write this as y equals 1x, and the 1 shows us that we're changing 1 meter per second. And then we started at 2 meters at the beginning. So y equals 1x plus 2 would be an equation that represents this graph. Now, this is really useful to answer questions like number 4, where we want the distance after 15 seconds. So in my equation, I'm going to copy it again. I had y equals 1x plus 2. And for those of you maybe thinking this to yourself, 1x is the same as x. You could just write that as x plus 2. That would be totally fine, also accurate. If we want to know the distance after 15 seconds, think back to your graph. We had on the x-axis over here, I'm going to label it, our x-axis was time, our y-axis was distance. So if I want 15 seconds, seconds was an x kind of value. That represents my time. So I'm going to replace that x with the amount of seconds that I know I'm interested in, which is 15. So we're going to substitute that in. We'll say y equals, when I do my substitution of 15 seconds, I'm going to put it in parentheses. And I kept everything else in my equation the same. And 1 times 15 plus 2 is going to be, 1 times 15 is 15, plus 2 is 17. So after 15 seconds, I would be at 17 meters in my distance, is my answer to number 4. So if you need to pause to catch up writing, to rewind and watch any of that again, please do so before going on to the next example. And before you go on to the next example, again, you may want to pause and copy down the graph so you can also mark on it along with me. In this graph, we do have the same setup. We've got time in seconds is our x-axis, and distance in meters is our y-axis. Notice this graph is decreasing. Over time, my distance is getting lower. So that's going to affect my rate of change. First question asked us our distance at the beginning. So remember, at the beginning is like your 0 term. So I look on my y-axis where the time is 0, and I see that I'm up at 8. So my distance at the beginning is 8 meters. And now, I told you last time I like to pick a nice point to compare to, but we're going to talk about this using proportions, that you might remember about proportions. So my next nice point I'm seeing on my line after my beginning value is over here at 2, 7. So we go down, I'm going to call down a negative direction, down 1 meter every time we go over 2 seconds. When we go to the right, that's a positive direction. So we go down 1 meter every 2 seconds, which means my rate of change, because we are going down, it's going to be negative 1/2. And now if we think about that in terms of what we're really saying, we're going down 0.5 meter per second. So check this out. You drop down 1/2 when you go over 1 second. So we can think about those in terms of proportions. So we lose 0.5 meter per second. So in our equation, we would write that as y equals negative 1/2 x plus 8. So again, the negative 1/2 is my rate of change. The 8 is my beginning value, or my 0 term. And now, just like before, if I want to use this equation, I can use it to help me answer questions now. So this problem is asking me about what happens, how far we would be at 12 seconds. So seconds, again, is my x unit. We're measuring time as our x variable. So I'm going to start with my equation, y equals negative 1/2 x plus 8. And because time is represented by x, I'm going to substitute 12 in place of that x. So I'm going to say y equals negative 1/2. When I substitute, I'm going to use parentheses, 12 seconds plus 8. And now I'm just basically simplifying. So negative 1/2 times 12, use a calculator if you need to. That's the same as dividing by negative 2, would be negative 6 plus 8 is going to be positive 2, and we're solving for meters. So after 12 seconds, we would be 2 meters away from whatever we're measuring as kind of our home base.